Right. Thank you. Okay, so I'm going to present the result of a performance gap study where we're comparing measured and predicted HTCs. I thought it was large. It's more than 500 buildings. It's 503, but more than 500. I was working with people who do stock assessment, and they thought it was tiny. So I thought I'd qualify it as quite large. So I come from a company called BuildTest Solutions, and we manufacture equipment to measure the energy performance of buildings. So heat transfer coefficient, U values, air tightness. We've done more than 120,000 measurements, or people have done more than 120,000 measurements with our tools, which is okay, but we want to do millions of measurements. Yeah, so the idea is to really scale up how many measurements we're doing. I'm sure this audience is keen on that idea too. I wanted to start off with a bit of context about who uses smart HTC. This is our product to measure heat transfer coefficients. It's been available since 2021. We've done 11,000 measurements. I say we, this is always our users. So our users use our tool to do 11,000 measurements, just over. We've got 102 different users, and it's kind of interesting to look at where they come from. So mostly they're sort of professionals providing consultancy services, so energy surveyors or consultants. I think integrators are a really interesting category there. It's a cloud-hosted calculator. We have a browser user interface which you can use to run data through it, but it's also available via APIs. I think that's how we can get really best scale in HTC measurements. This is all using monitored energy and internal temperature data. We've just produced a method which uses only energy data because we found loads of people had temperature data, loads of people had energy data. Not so many people had both. So that could be even better for scale, I think. But of course, every time you take up some input data, you lose some accuracy and some precision. I want to race through these so I can show the results more, so more interesting. Just put this in because when I show you the results of our performance gap study, I want you to really believe that it did mean something. Yeah. So this is 4C3 comparisons between smart HTC, which is an in-use energy balance. So it's while the building's occupied using onboard data, and co-heat tests. And it's quite a varied sample of buildings. So the heat loss parameter varies from really low, 0.7 active house standard, to 4.4, which is incredibly high, almost 10 level thermal performance. And we've got good accuracy. And here I'm using the net mean bias error of -1, so 0% would be perfect accuracy here. I presented this in some commercial settings recently, and everyone says, "Oh my God, you're only 1% accurate." Oh, no, that's ideal. But that says we don't have a significant bias to over or underestimating, and we have reasonably high precision. So 12%, that's how close we are to the right answer on average. It's competitive with other methods, but I think you can see there is still some uncertainty in the result. And then I wanted to reflect on what we're comparing it with. So RDSAP, Reduced Data Standard Assessment Procedure, is the UK standard method for producing energy performance certificates. It's not super special, and I'm sure it's almost the same as every other country's method. It's also the same as any other PHPP or, times the U value by an area together. It's done by assuming the performance of a particular construction type based on looking at it. Yeah, so I look at the brick structure and say, this is a solid wall, and therefore, on average, solid walls have a U value of this. But in this room, we know that they're actually extremely variable. Okay, so when all of our inputs have uncertainty in them, of course, the outputs have uncertainty as well. And what's really frustrating, and I think something that we as a group really need to campaign for, is in the UK, there is an accessible via API database of EPC data, which is actually great. Okay, it's a really positive thing. But we don't store all of the inputs in it. we store some of the inputs. So you can almost recreate the EPC, but you can't recreate the EPC. We also don't store the HTC. So when I measure an HTC and the building has an energy performance certificate, in the process of generating that energy performance certificate, the HTC was calculated, but we didn't store it and we didn't store the inputs that are necessary to recreate it. So when we come to do the measurements, when we did this study, it was actually just as difficult to get the modeled HTCs as the measured HTCs, which is crazy because every single building had already had it done already. So we really need to lobby that this is an important metric and we should feature it prominently in our energy performance certificates. Well, it doesn't even really need to be on the certificate itself, but it needs to be somewhere where we can compare. And then on the right-hand side here is our sample of buildings that we did our performance gap study on. I think the one thing to highlight is it's focused more on older buildings, existing buildings, not so many new builds. Most performance gap studies are focused on new builds, and this is more like the opposite, older buildings. So we had a total sample of more than 500, 103, with its bias towards older buildings. And when I first saw this chart, I was so sad. I really wanted this to be a point cloud that said, EPCs are ridiculous, they can't predict anything. There's no correlation with measured performance. But gradually I've come to terms that actually it does an okay job of categorizing best, middle, worst. Yeah. But actually only 50% of the predictions come within the only 57% of the predictions, 57% of the predictions fall outside the confidence interval of the measurement. So it's not bad on average, but more than half of the time we're wrong. Okay. And of those that are outside the confidence interval, so those 57%, 72% of them were better than predicted. So there was a bias to the buildings being better than we predicted in the EPC. But a bias, there are also a lot that were worse than predicted. And the average performance gap, which is the average absolute gap, is 30%. So on average, we're 30% away from the likely side with our prediction. And sort of remember the shape of that chart. We'll come back later. So here's on the left-hand side how big the performance gap, the gap between the predicted and the measured HTC was. And so here's our 53% of within 25% of the right answer. So half of them are really wrong. And some of them are really, really long. 2% of them were more than 100% different. So the prediction was total rubbish. There's almost no point having it. And then here's the HTC by SAT rating band. So an A-rated building is the best energy performance, has the lowest energy cost. And it's nice that they actually do scale, okay? So the best predicted buildings were the best measured buildings, but they also have the biggest performance gap. But the sample of that is really small. And these buildings in the middle all get a little bit similar to each other. The lighter grey is the measured HTC. So B, C, D, E, they're all quite similar to each other, which is something that we found in the when people have looked at energy consumption. Those buildings, they're all a bit samey. 2 minutes, Rich. Perfect. 2 slides, 2 minutes. So I also looked at all the previous performance gap studies where I can compare HTC measured and predicted. And these are Leeds Becker, Builder Performance Network, and the Desmes Smita project. Now, this is a sample of 84 buildings biased more towards new builds. And here, 70% of the measurements were outside the confidence interval, so we were only like 30% of the time. But 85% of them were worse than predicted. Okay, so in this case, it was more common for the buildings to be worse than predicted. So new builds can struggle more to match predictions. The average performance gap was 31%, and it was 30% in our sample of 500. And this trend line has almost exactly the same characteristics as the previous, as my new sample of 503. So that says something that the results are a little bit repeatable, I think, which is kind of interesting. So this final chart is all of those buildings together. So now we're at about 600. And I thought, what do I make of it? You know, now we've done this comparison, what learnings do I draw? So the accuracy of RD-SAT was 8%, which actually is pretty good, I thought. It's not particularly biased towards over or underestimating. Slightly biased towards actually under predicting how good the buildings are, tend to be a little bit better than expected. But the precision's pretty poor, 38%. We can do 12% with measurement. So there's a big opportunity to have more precision. Okay. So what that means, I think, is for groups of buildings, the predictions are useful. They help us to categorize which buildings are best and worst. But for individual buildings, the prediction is not a very good tool. So if we're thinking about what to do with a particular building or what size heat pump it needs, then a prediction starts to be a really weak tool. And one of the analysis that was done from this performance gap study was to think about what does this mean for retrofit spending. So in the UK, we have a target that every building should reach EPCC. And the analysis suggested that because there were loads of buildings which had already reached EPCC, which would receive funding in order to meet it, because we've miscalculated their energy performance, there was £60 billion worth of misspent retrofit spending that could be spent somewhere else on the buildings that really do need it, that we thought were okay but aren't. So that's the cost of getting the predictions wrong. I think it's poor for quality assurance. If we do some retrofit measures, the EPC isn't a good enough tool to tell if it works. We need to measure in situ to make that argument. And it's poor for heating and cooling styling. We don't know for an individual building what the demand is. So these are the opportunities, I think, where HTC measurement has real value. Yeah, especially in this policy field where the retrofit policy, I think, struggles a little bit because it struggles to really demonstrate clearly how much value it has. But it's got £60 billion worth.
The extra minute. Who's next?
I'll go.
On next one.
You should get it.